Good morning, everyone. My name is Long Gong, and today I'm going to present this paper titled Arming the Next Generation of Spaceflight Embedded Platforms Through Processor Reusability. And this work was conducted by Kayla Henderson and her team at the Southwest Research Institute and was published in the 2023 IEEE Aerospace Conference. Here's a quick overview of today's presentation. We will start with the background and motivation behind the research, followed by the proposed unified processor architecture. Then we will explore how power management is handled, the benchmarking methodology used, and the key results. Finally, I will share some conclusions, limitations, and suggest directions for future work. Space missions are demanding increasingly powerful and efficient onboard computing systems. Traditionally, different missions use different processors, customized for each specific use case. This drives up both cost and development time. Every time a new processor is used, engineers have to rebuild software stacks, drivers, and verification systems from scratch. This paper asks a bold question. What if we could use just one processor architecture, an ARM Cortex-A72, for all spaceflight embedded platforms? By using techniques like power gating and frequency scaling, the authors aim to make a single processor flexible enough to handle a wide variety of mission profiles. Why a single architecture? Because using the same instruction set and optimization strategies across missions enables code reuse, faster development, and a shallower learning curve for engineers. The Cortex-A72 supports key features like power gating and clock gating, allowing you to shut off unused cores or components dynamically. It also supports scalable frequency control from 700 MHz to 1.6 GHz, meaning you can treat performance from power efficiency. And because it's Linux compatible, you can customize a single Linux image for all missions, saving a massive amount of time. Now let's talk about power. ARM's architecture includes independent power domains, one for each CPU core, the L2 cache, and debug clocks. The processor supports ultra-low power idle states using instructions like WFI and WFE, allowing it to stay responsive while minimizing energy use. It can also clean L2 cache or handle minor events without fully waking up a core. Dynamic clock gating at both regional and global levels allows selective shutdown of unused logic, enabling fine-grained power optimization for diverse mission profiles. The authors tested their hypothesis through multiple benchmark categories. First, they ran synthetic benchmarks like Drystone, Whitestone, and Cormac to measure core-level performance. Second, they used JPEG-LS, a lossless image compression algorithm important for space image missions. Third, they tested mobile net SSD, a deep learning model used for object detection on the COCO 2017 dataset, using ARM-NN and TensorFlow Lite backends. For comparison, they evaluated ARM Cortex-A72 against the GR712RC, MPC8548E, and UT699, three processors commonly used in current space systems. The results were impressive. At 800 MHz, the ARM processor achieved a core mark score of 18,643, compared to 3,511 for the MPC 8548E, a 5 times 3 increase. It also beat legacy chip in DMIPS per megahertz and MWIPS per megahertz. Core mark scaled almost linearly with the number of active cores, showing that multi-core utilization is effective. Across frequency from 700 to 1600 MHz, the processor maintained stable performance per megahertz, confirming frequency scalability. And in the GPAC-LS compression task, the Cortex-A72 outperformed again. It encoded an 8 megabit grayscale image in just 414.6 milliseconds compared to 8,615 milliseconds for the MPC 8548E. Decoding times were also more than 20 times faster. Most importantly, the outputs were beta exact, meaning the ARM processor preserved data integrity while achieving massive performance gains. And on the edge machine learning task, the ARM chips again delivered. With the ARM NN backend running float 32 per session, it achieved 8.88 frames per second throughput and 113 milliseconds latency. TensorFlow Lite was slightly slower, and Int8 offered lower accuracy, 19.3% mean average precision versus 22.7% for float 32. These results show that Cortex-A72 can run real-world machine learning workloads effectively without dedicated accelerators, which is crucial for onboard inference in satellite or robotic missions. To summarize, the Cortex-A72 is a viable candidate for next-generation spaceflight embedded platforms. It offers high performance, scalable power modes, and strong software reuse potential, making it an excellent all-in-one solution. However, it does have limitations. It's not ideal for ultra-low power missions that require sub-minor 1.5 watt operation, where chips like GR712RC still hold an edge. And the authors suggest several next steps. First, run long-duration benchmarks over hours or days to study thermal and powerful drift. Second, conduct radiation harness testing to verify stability in high radiation environments like deep space. Third, explore integrating heterogeneous accelerators such as GPUs or FPGAs. And finally, optimize sub-block power gating for even finer control over standby power. And that concludes my presentation. Thank you for your attention, and I'd be happy to take any questions you may have.